Hey guys, hope you had a good Easter, had a good time with your families. Um, you started reading chapter 12 on Friday, Thursday, whatever day it was. Anyway, we're going to start a chapter on temperature and thermal energy. I wanted to start out just giving you a little bit of a historical background. Um, our present theory of how we understand thermal energy is based off of a theory that was basically around since Aristotle, 300 BC, in different forms. The old theory was called caloric or caloric theory. Um, it was based on some strange things, and even though it was dead wrong, it was good because it allowed people to understand just exactly how thermal energy did go from one object to another. It was incorrect, but they had parts of it that was very good. Um, to give you an idea of what it was, uh, they believed that thermal energy was like something that was in a substance. So it was like a fluid. And it was part of everything. All matter had this fluid in it. And to give you an example, um, there would be caloric in my hands. So if I rub my hands together, that caloric comes to the surface and my hands get warm. And then if I touch something else, like say a cheek or something like that, that gets warm also. So it was the way that they explained how thermal energy was transferred. Now, this fluid, it was almost supernatural. It was colorless, odorless, tasteless, massless. Um, it was basically not observable. Um, I gave you a video to watch of Benjamin Thompson, Count Rumford. He was one of the first to really question the theory. He was in charge of boring of a cannon factory, and he made some observations that just didn't make sense with what the present um, um, theory was. So take a look at that. It's kind of interesting. It gives you a little bit of history, which is good for us to have. Okay, let's take a look at our current one. Our current model of thermal energy is based solely on one of the pillars in science called the kinetic molecular theory. You studied it last year in depth. It has two basic components to it, and it's very, very simple. The first postulate is that all matter is made up of particles in constant motion with elastic collisions. We know elastic collisions mean that there is no loss of kinetic energy. Whatever kinetic energy we start with, you end with, and that is very important. There's also a three-way relationship between motion of particles and the kinetic energy that they have and the temperature of the substance. Those three things are directly related to each other. Now, when we look at a substance, doesn't matter if it's a solid, liquid, or gas, there's some things that they have in common. The substance is made up of particles. You see them here in the blue. And there's also bonds between the particles. Thermal energy talks about both of them. When it comes to motion, we know solid, liquids, gases. The solids have very little motion, very little kinetic energy. Basically, we say they vibrate back and forth about a fixed equilibrium position. Where if you're a liquid, you have some freedom. You can rotate or spin. There isn't a lot of difference in volume of the solid and the liquid, but the particles aren't held as tightly in place. That's why we say that fluids can take over the shape of a container, the bottom part of the container. If you're a gas, on the other hand, the bonds are almost non-existent, and you are able to vibrate just like the solids and spin and rotate like the liquids, but now you can translate. You can move in a straight line. We have to consider both of those. The kinetic is the motion. The potential is the bond strength. So it's a sum total of all of those energies that make up what we call thermal energy. If you look at the particles of a substance at a lower temperature versus a substance at a higher temperature, the main difference is You can tell the velocity vectors in red. The one that has at a higher temperature has more kinetic energy, more collisions going on. Definition-wise, thermal energy, I like the definition in the red, total internal energy. That includes all of the potential, all of the kinetic associated with the motions and arrangement of the particles. Heat, on the other hand, most people goof that up. They say they're synonymous. Understand the key term for heat is flowing or energy in transit. Heat doesn't happen if you don't have energy flowing from one substance to another. So if something's colder, it's going to absorb thermal energy. If something's warmer and it comes in contact with a colder object, it's going to give it off. This flowing of thermal energy we call heat, and that takes some kind of thermal contact, whether it's conduction, convection, or radiation. Temperature we already talked about. The key with temperature, average kinetic energy, and it's a measure of an object's ability to give off or absorb thermal energy. That's why it's so important. Temperature will be probably a little different for us because it's one of the first indirect measurements that we actually make. It's impossible for us to measure this kinetic energy directly. We don't have the technology. And because even if we did, the kinetic energies are so different because of the collisions that are taking place all of the time. So what we do is we say, okay, we want to talk about the temperature of an object. Well, we're going to measure what it does to an object. The higher the temperature, the more the motion of the objects. They're moving faster. And if they're moving faster, they're moving further apart because they have inertia. And the more they move, the more inertia they're going to have, the more it's going to take to change their direction. So what we do is we measure temperature by a change in volume. Old school, we have a thermometer with some kind of a fluid in it. As it increases in temperature, it increases in motion, it expands. We read that expansion and give it a temperature rating. Nowadays, we go more with electrical resistance. I like the new thermometers that we use. In them is a little component called a thermistor. I don't know why it's not a thermostat, but it's a thermistor. Anyway, that measures the change in electrical resistance due to the temperature of an object. And now it takes that resistance and we give that a temperature reading. There's many different kinds of temperature scales. You're tempted to think that Kelvin's absolutely the best, and it probably is, and Celsius is good, and Fahrenheit should never be used. But really, there's nothing wrong with any of the temperature scales. And unfortunately, so many different companies, businesses, and people use a variety of them, so you need to become comfortable with them. And we'll spend the next couple days working on that a little bit. As you go through my notes, guys, if you take a look at this slide right here, what I'd like you to see is, to me, 180 is the magic number. And if you can think of boiling of water, because everybody knows that, you need to get to 180. And that'll tell you what the formula is going to be, right? And look at this. We'll talk a little bit more about that tomorrow. Guys, have a good day and just hang in there, guys.